All right, so welcome back to our Cyber Physical Systems course. We are going through Chapter 3, and that covers details of cyber physical systems. And we are going specifically at this point in the chapter, we're going through some ideas on possible applications of cyber physical systems. We saw energy and advanced automobile systems in the previous session, and now we're going to talk a little bit about consumer electronics and what type of opportunities and systems fall in the domain of consumer electronics directly. So one has to do with RFID. So RFID is perhaps one of the least tapped for potential when it comes to technology on things that could integrate, connect, and identify anything and everything to anything and everything else that is connected in the internet. So, and that can have a lot of great repercussions and bring a lot of opportunities to things like infotainment. So this is the mixture of information with entertainment, so that if we have some type of identification on us that can be recognized wirelessly through RFID, then as we approach different kiosks or different devices, content could be tailored to the person from an information and or entertainment perspective. The other one is banking, so from a payment perspective, and I think that is where RFID probably has the most potential, and I think that's why it hasn't caught on very much, because people are reluctant. People are reluctant to give up that control when it comes to their money, but that's where most of the potential of RFID technology is. And when I talk about RFID, I mean I'm talking about the near field type. There are three standards or three tiers of given the different distances that you can have for RFID. The one that has the most potential, and probably your phone has already built in that technology, is near field communications. Actually the range is just a few millimeters. And we don't want any more than that, because if we're going to be executing payment and highly secure transaction, one way of privatize and secure those transactions is by limiting the range. So near field communications are only designed for just a few millimeters. You put your card or you put your phone near the terminal and you can execute payment transactions. So these are just a few, but there are many more. Of course, we would like to identify assets of all classes, and not only identify them, but also track them for inventory control, for logistics control purposes. So RFID also has a home in those applications, as well as energy. So energy is one that we're going to talk about specifically as one of the areas and domains where cyber physical systems can play a role to make things a lot better. So normally anything that has to do with infrastructure, all these things that we're talking about, whether it is banking, energy, entertainment, and information, these are big infrastructures that actually they play a big role in our everyday lives. So we're not talking about niche markets. We are talking about broad markets that can really change dramatically with this type of complex systems and technology. So including retailing. So there is an example here where you can identify products that you want to buy, whether it is in a storefront, for example, but there is a close correlation with e-commerce and or there is a tight integration between storefronts and e-commerce, so you can be delivering information as you, let's say, approach some type of article that you want to buy at a store. So you can see that big companies that basically became big in pure e-commerce, they are going forward with this more omni-channel approaches. So you can see Amazon now, they're looking more at having retail space through the supermarket chain that they bought, but they are looking at more than that. So they have realized that it's not one or the other. It's not brick and mortar or e-commerce. It's actually an omni-channel. So consumers want to have access to both, and they want both to be integrated seamlessly. And that's going to take very smart and complex systems to make that happen, from an identification, asset tracking, and software perspective. So for example, if you are in a store and you approach a device and your phone can recognize the ID, and that rack with these devices has also a terminal that can recognize you because you also have an ID that is wireless. Now we can communicate. The terminal can know what you like, and you also may want to know some information about that particular product, and you can get the information very specifically tailored to answer your questions and make your experience, your buying experience better. So now let's talk about energy, which is a big part of where cyber-physical systems can play a big role in making things better. We have been talking about smart grid for a while, and I'll talk a little bit about that. And it hasn't expanded, or it hasn't advanced as rapidly as some of us had hoped, because the stakes are very big, and the infrastructure, the entrenched infrastructure, and the capital investment that had been made is huge. So it takes time to change, but the catalyst that complex cyber-physical systems can offer can make it so that change goes faster from now on. So what are the areas that can benefit from more intelligence, better sensors, network-connected sensors? What are the areas that can benefit, that are a big part of the energy infrastructure? So obviously efficiency. So efficiency is, there is a lot of still wasted energy in the world. Reliability, that's another one. We still tend to lose power often, even in very advanced societies, we tend to lose power often. And then if the network and the grid is going to be smart, remember what I said at the beginning during the first chapter, that the smarter the system is, the higher the propensity to be open to attacks, because you have to connect and you have to be open to other systems to derive that intelligence. So that makes you more vulnerable to attacks. So security is a big part, as well as stability, reliability of the overall complex system. But if we achieve that, then we can have an overall more sustainable infrastructure. And when we talk about sustainability, we're really talking more than just green and those kind of concepts. Really sustainable in terms of reliability, robustness, and of course, efficiency. So what are the two main research areas? So you get an idea how people are researching for opportunities to apply the ideas of cyber-physical systems in the energy domain. One is the power grid. So the current power grid is not designed to support high variability in supply and demand. It's pretty static. And if you take a course in power systems at the grid level, you'll see that those equations are pretty much like circuits equations, and they're very static in nature. And we'll see in the next couple of slides how they approach that, because they still have to account for variability in the load, and that's one of the big challenges. But because we are not as efficient as we could be, then there is a big opportunity to save money, to save costs in power bill. Energy consumption, and the fact, mainly in the United States, where people tend to have these big houses, is a huge amount. In the summer, some people pay for their electricity bill $700 a month, and that's not unheard of when you consider your pool, your finished basement, you know, 2 stories. I mean, that it can add up very quickly when it's 95 outside for those couple of months, and it really disrupts the budget of people. That trickles into the economy, because if you have a surge of expense, then you're going to basically tighten your the amount of money that you spend. So it has a lot of repercussions downstream. So having a stable and predictable and more efficient supply and demand matching in energy is very important, and it could really improve the economy. So what that requires are better control, better efficiency, better management, and to get that, the best way is through modeling, which is one of the big themes that we've been saying over and over again, through modeling. And being able, if you're going to model high intelligence, it is because you are trying to model a system where high data availability exists. So you can actually get a lot of data, so you can do something with it and improve the system, control it better, make it more efficient. So that means that we need to have all kinds of sensors deployed that are going to be connected and in different configurations and different topologies to be able to get the information that these new algorithms would need to make all this happen. So that would give you, for example, better control to segment the grid into things like microgrids. If there is a high concentration of houses with solar panels that are overproducing energy, it may be that you can make sort of a microgrid, and that section of the population can sort of be self-sufficient if the load and the supply can be balanced. So all kinds of ideas and all kinds of algorithms can be come up with to make this happen. So what do we do today? So today we have 3 types of generators or set of generators. So the power company, they have base load, a base load which runs all the time, and that provides the minimum level of demand with good efficiency. So these are your best, most efficient generators, and therefore the most expensive ones. So you run those for minimum load. Then you have an intermediate load that runs often to sort of satisfy some average of demand. And then you have the peak load generators, So those that you can start and turn out fast and maybe are not so efficient, those you run it to satisfy the maximum load. So among these three tiers, you try to establish some type of load balance, but it's open loop. It's open loop. And it still fails if there are big surges of demand. So they're not very reactive because the control is not there. Now, when you add to that renewable energy assets and resources, those are even more unpredictable. So that's on the, not on the demand side, but on the supply side, because they rely on the weather. Whether we're using wind generation, or we're using solar generation, or tidal energy, they all depend on the weather and the environment. And that we cannot obviously control. So it's hard to integrate that extra supply into the overall demand equation so that you can achieve to a better and more efficient balance. So being able to have access to the grid as a network rather than as a distribution of energy allows you to control and receive and know what's going on at every point of that network and use sophisticated algorithms to balance the demand equation, the supply-demand equation much better. For example, integrating energy that people are overproducing and integrating that with their billing. So some of those things are available, but they're not as, so a lot of these ideas and technologies that we are talking about, that doesn't mean that it doesn't exist. But just because something exists at a very low level of what we would call pervasiveness or market penetration, that means that still a lot of work needs to be done, okay? So, for example, in the country, solar is underutilized because it's still too expensive, too cumbersome, okay? We see more, for example, here in New Jersey than we see in Florida, where there is more sunshine, because Florida doesn't subsidize it, but New Jersey subsidizes it. And that's fine, that's just a policy situation, but it should be that, how come that in Florida, where there is a lot of sunshine, you don't see half the solar panels that you see in New Jersey, when it's going to start getting like cloudy every day in a couple of months? So we need to get to that point that is pervasive. So when something is pervasive, then we know that we have arrived. And just because we have it a little bit, well, that's not good enough. We need to work on these technologies to make it happen in a big way, in a big way. So a smart grid, what are the things that we could do? So again, embedding sensing and intelligence all over the network. So now we're not talking about a grid, we're talking about this network where energy is just part of what is traversing the network. There is also data, there is also intelligence going through all the nodes. Imagine that type of cyber-physical system where you have the environment, if you have wind and solar and tidal and so on, and geothermal and whatnot, if you have the environment and you have people, because people rely on energy, and you have the actual energy grid, but then you have this network of data and intelligence. So that's a huge cyber-physical system, where the physical part is the environment and the people. So at that point, what we can do is very granularly make better decisions because when you can make better decisions, or when you can make decisions that apply to a smaller section of your system, you can tailor better and optimize the outcome of those decisions instead of sort of painting with a broad brush, which is what we do now. Okay, it's sort of a broad brush approach. So you can then and better tailor the decisions to what is going to have the best effect. So again, supply, load balancing, and of course pricing. So there is still a lot of research going on when it comes to different sensors for the grid and materials. So there is a lot of these sensors. They have to be exposed to the weather, and how do we do that? As well as algorithms. That's the biggest part. The algorithms that will be able to comprehend, and the way to come up with these algorithms and make them better is through modeling. So if we get there, when we get there, we'll see a smart grid that integrates all this infrastructure, all these devices that can plug into that network of energy and data, all kinds of sensors, always of smart metering, so we can actually, for example, tell someone, if you turn off your appliances or certain number of what you are using, so we don't have to dispatch another generator, you'll get a credit. Now there are some programs from the energy companies, but what they do is they take over your electricity, and actually they do it for the AC now, and you can sign up for a program on some electric utilities where they put something on your AC and they control it, and they give you a credit if you allow them to essentially control it so they can manage the load better. Well, that hasn't been very effective. A lot of people have not signed up for that. And why is that? Because it's a broad brush. Now you're telling everybody, we're going to treat you the same way without customizing that for the needs that they may have. So when people are going to sign up for something like this, is if it becomes a collaborative decision-making process. Because maybe someday you can say, sure, shut it off, but maybe some other day, you have your baby in the house and it's too hot and the baby's uncomfortable and starts crying. You don't want to do it that day. So you cannot just give up that control. That's why it hasn't worked, because it's a broad brush. But with this more intelligent systems, with data can flow seamlessly and we are all connected, then we can make these better decisions at a very micro level. And that's when it's effective, when it's tailored to the situation rather than a broad brush approach. That's what we call adaptive. We call it adaptive because we can adapt instead of just being a matter of policy. It's a matter of adaptation and a closed loop control system. So that obviously is more cost effective. Why? Because more people will accept it. More people will accept it, and they will be more efficient and resilient. So you give people and get them involved in managing their own energy consumption rather than either it is what it is or giving all the control up to the power companies. So that also allows for optimizing market cost. So there are many generation facilities of of course, geographically distributed, but energy has different costs in different places. And then part of the energy consumption, as we have more, of course, all these algorithms and all these facilities, what also grows is infrastructure, computational infrastructure, let's say servers and server farms. Those have to grow as well to help us, and part of the implementation of these huge cyber-physical systems. If we can realize that the cost of the ongoing energy costs is much higher than the one-time capital expenditure, let's say, of hardware, you can have replication of server farms of this type. And then you can basically move the load to where electricity or energy is less expensive at the moment. So that is a business case that can also be modeled. So it opens up all kinds of possibilities. So the other one being a simpler one. So lower the temperature in a room where no people are in it. So it takes time to heat up the room. So you have to now predict when people are going to come in. And how do you do that? And if you mispredicted, people get really, really upset. People don't like to be uncomfortable. So think about, with all the technology we have, how much more is there to be done? We just had a new AC system put in. Doesn't seem to me that it's very smart. When I came this morning, it was freezing. I came in at like 7:30. It was freezing for some reason. It's a little bit warm at this time. It's a new system. It's not like they just put it over the summer. Okay? There is a lot of work to be done to bring more intelligence, and that making systems smarter. And the reason they're not smarter is because complexity takes this discipline and methodology to put together and make successful. The modeling, the good systems engineering approach. It's not happening as fast as it should because projects are failing. They're trying to have more complexity with the methodologies of long time ago. It's not going to work going forward. We have to look at all the more advanced methodologies that we're talking about in this course. All right, so now let's talk about infrastructure. Even though energy is one type of infrastructure, and you can talk about infrastructure in general because there may be some themes or modalities that apply to all of them, whether we're talking about energy, education, transportation, all the big things. So if you want to think about big things, these are the things that people take for granted, that you don't think about. They are there, and you only miss them, you only notice them when you miss them. They're not there. But they are very complex. That's what makes modern life possible. So let's talk about critical infrastructure and what are the common modalities that apply to critical infrastructures, the ones that we cannot do without. These are also ripe for infusing the benefits of cyber-physical systems holistically because they have complex interdependencies. This is all of our modern life, if you will. How do we network all that and sense it up, collect it up, compute it up, and then control it up? So all of that, all this set of different complex infrastructures. The common modalities beyond the interdependencies that they have is cybersecurity, because again, complexity begets vulnerability, and human interaction. Which are hard to model. These are some of those critical infrastructures. Food generation and distribution, electricity, financial services, gas production, transportation and distribution, heating, oil products, public health, security service like police and military, telecommunication, transportation, all of transportation, including railways, airports, harbors, and water supply. So if you want to come up with a solution that has staying power and is attractive, and that you can, if you can offer a benefit that outweighs the entrenched investment, and that's not easy to do, then you have a winning business case. So let's pick one of them and talk about banking, for example. Banking is pretty archaic. I mean, we have the ATMs and we have the drive-throughs and all that. But if you walk into a bank and you're going to make a withdrawal, they don't trust you with any of that. You have to show your driver license and actually write it out. You have to write out the number, 3,400, and you have to write it out with your own hands. That's archaic. Why is that? Because we don't trust the technology. The technology is there, but we're talking about how do we get to have a technology that is secure enough for someone to say, for the business people that own the bank that are not technology savvy, to say, oh sure, you know, that ID, that label, RFID, your phone, that's okay. Just push it up through here and here your $3,000 out of your account. We trust that it's you and we know that everything is okay. So if you come up with that type of system, which is complex and secure, then it's better for everybody. I mean, fewer lines at the counters, perhaps fewer people at the bank, and they have to, you know, retrain and do something maybe more interesting. But there is an opportunity there. So Apple has seen that, and Apple Pay is one of the most promising systems. And Apple is just going to make it secure and work on keeping it secure for a modest 0.15% per transaction. You won't even feel it. I mean, so that's just to put in perspective, that is a tenth and a half of a penny on each dollar. So you have to spend $10 and you spend 1.5 cents. And to spend 15 cents, you have to spend $100. 15 cents on $100. People won't care. But Apple knows that they're going to make $5.5 billion a year on Apple Pay as they ramp it up. So that's a good business, because it's something that applies to a lot of people. So that's just an example. So to make this the key, as we're going to see in the next chapter a little bit as well, when we discuss Internet of Things in more details, IoT, or Internet of Things, is the underlying approach or paradigm to make all this possible, because it's the network backbone to connect all these things of this critical infrastructure together. And then the idea is to have resiliency. So we're defining here resiliency as more than just smart. It's smart and secure. Okay? So remember that. And the way to get there is by good conceptualization work, a lot of thinking and measuring before coding. When are we going to learn that? So I don't know if you're familiar with the anecdote that Michelangelo spent many months just staring at the rock before making the statue of David. And when he was asked, "What are you doing?" he said, I'm working. He just went to his studio and sat in front of the big hunk of marble and stared at it, visualizing, thinking. It took him a lot longer to conceptualize and think what he was going to do than actually carving. When he had this clear and well planned, then he did a masterpiece of a job. So we have to be more like that. Think ahead more, not be seduced by the instant gratification of getting something done and getting some feedback. We have to be more secure in ourselves that, hey, we're going to take our time, we're going to plan, we're going to model, so we don't have to do more rework. So that goes for all types of projects and sizes of projects, but where it has the most consequences not to do it that way is in this complex systems. Now let's talk about healthcare. That's a big one. That's another one that is, at least from a networking and data perspective, so archaic. Everything is on paper. People have these charts, and you go to a physician's office and they have rooms with file cabinets and all these papers. And that's not all of it. I mean, every so often they have to move it to a facility to store more paper, patient records. So, and since it's paper, of course, doesn't interoperate with anything else. There is a humongous waste of time that people are spending on healthcare. I'm not talking about the actual go have your procedure or your consult done. No, you go there and you wait for an hour, 45 minutes, because it's not optimized. It's not the logistics are catastrophic. Nowhere optimized at all, because there are no good systems in place. There are no good systems in place. Now, when it comes to devices, we do have some very good devices, electronic devices, and there is a lot of high tech in the medical devices. And if you go, I hope it doesn't have to be for real, but if you saw a picture of an intensive care facility, it's amazing the amount of electronics that is available. Okay? So the technology is there, but it's segregated, it's isolated, and it could be better if it was networked. So there's no interoperability. A lot of it is proprietary, so the usage, since interoperability is not a concern or a desire, then standards don't tend to be used a lot. And so there are a lot of proprietary technologies. Now, again, you have to balance the investment on R&D, and some companies may want to do things proprietarily to defend what they're doing. So there's also a business aspect there. I'm not saying everything has to be open, but we could be doing better when it comes to balance those two. Because those medical devices still rely a lot on human input. So we could be taking a lot more data and making more decisions or better decisions for the patient as part of using those devices. So this puts a lot of stress. This puts a lot of stress in the medical community, nurses, physicians, and that leads to errors. Because they lead to errors, that either leads to bad things happening that maybe we don't even know about. And the ones that we do find about, then those become very expensive litigation, and insurance is very expensive therefore, and that's just a cost on society. That's part of the high cost of healthcare. So there is a part for these smarter medical devices to play to even influence the cost of healthcare. So the strategic R&D right now, what they're focusing on is high confidence networking and information and communication technology. So that's ICT. Applied to things like certification, so of the devices, the design and implementation, so of these devices. So how do we apply, now that we know how to make these great devices, how do we network them with resiliency, high confidence, high security, so they can operate and interoperate better? So that's going to take a mixture of wireless and wired communication infrastructure. So to do that, the barriers are in this relevant domains, and that's where the barriers must come down. These are the domains. We're gonna have to learn how to design better cyber-physical systems by checking and reasoning about their properties. So that's part of the flow of requirements, gathering and generation, and functional analysis, which we have discussed in more than one occasion. We're going to have to use more computational models to support the effort and the discipline of systems engineering. And we have to implement the technologies, that's a given. But we're going to have to also, instead of using ad hoc modeling, use a more mathematical concept-based modeling. And I want to keep saying and making it clear that I don't mean equations. This stuff is too complex to put in terms of an equation, which two sides of an equal sign. No, you cannot do that. But you can think in terms of state variable or state machine design. All those have a mathematical concept and foundation behind it, and they're very important. So also, medical robotics, that's another area that needs to be improved. And to make all that happen, then real-time computation. So the real-time aspects that we talked about in the last chapter, and at the beginning of this one, the real-time aspects, that needs to be comprehended better in the design flows. Right now, remember we discussed that the languages that support modeling and design and implementation, they don't support real-time methodologies, and they don't have real-time constructs for software. So in the future, what we want are these high-confidence cyber-physical systems that are used to put together these medical devices that they can cooperate with each other and coordinate with each other. They're going to be very heterogeneous and configurable, and so they can be personalized for the patient. Again, the trend is this micro customization, but without the cost that normally is attached to customization. So one way to make things less expensive is to apply the same thing to many people, because you spread out the investment and the costs over a large number of users. But so when you want something very customized, it costs you a lot of money, because you're the only one that is paying for it. So those are the extremes. So what we want is, how do we get that customization that does indeed add benefits with the cost of something being done for the masses? That is the trick and the goal. So we want this patient-centric autonomous systems with good performance, and also seamless supervisory control, so that basically we have access to the information of what is going on. So the research challenges for these types of systems are high performance, high confidence cyber-physical systems, so HPHC CPS, high performance, high confidence cyber-physical systems. The key is networking and real-time sensing of the physiology of the patient, control and feedback to that supervisory system. Some of the technologies associated with that, sensor fusion, that is taking data, the same type of data from different sensors, and being able to, through an algorithm, be able to come up with a better inference than if you had only one type of sensor. So that's sensor fusion. Another area that can benefit is prosthetics, so smart prosthetics, and minimally invasive diagnostics and intervention technologies for medical procedures. If we can do all that with better control and feedback, then we're onto something. So these are the challenges, and with the research of this high performance, high confidence cyber physical systems is taking place. An example is precision microsurgery. So we have ways to architect and manufacture what is called MEMS, micro electromechanical systems and devices, and NEMS, nano electromechanical systems and devices. So obviously nano is smaller than micro. So imagine a device, Now these devices are very small, so they take very little energy. But imagine if these devices could be inserted, instead of a big surgery, inserted into a patient to basically eradicate some type of clot or fix a weak artery, and introduce that, or maybe modify the electrical impulses that we know are causing some type of symptom like tachycardia of the heart, for example. So there are a lot of opportunities for these complex systems to be fabricated and made small. The fact that they are small actually makes them more complex. So again, sometimes complexity and size are correlated, but that's not really the norm. You can have very complex, small devices and systems. So if we can do that with less invasiveness, that's just better for the patient, right? Because now we have to do less damage to tissue around where the procedure is taking place. And I'm sure that there are statistics for how many of those procedures don't turn out well. Well, those statistics could be lower, and that's good. That's good for everybody. So there's good motivation and good opportunities when it comes to healthcare, microsurgery, as an example here. How about the idea of what's called smart dust, which is these small particles that you can, or these small systems and devices you can just put in clothing to be able to sense different things from people and be part of this network of information, so we could be more into we could anticipate diseases and illness sooner. That may have a lot of that could do a lot of good for infants that cannot tell what's going on with them, and when you actually notice that they're sick, it's well advanced, because they cannot tell you as soon as something starts hurting. So for infant care, the application and of smart sensors to be able to anticipate proactively illness is a great area of application in healthcare. Now let's take a more specific view to the example of a pacemaker. So you see how it's sort of done now. We're kind of trying to change that, and how it could be done in the future, and what are the tools that you need to use to come up with a design that is relevant, a relevant complex cyber-physical system per today's standards and what we're talking about in here. So a little bit about the heart. So the heart is an involuntary muscle that pumps blood, and the signal comes from the brain and is programmed pretty much with a rhythm, with a normal rhythm that varies about 100 beats per second. I mean, per minute. So the heart has this natural pacemaker that makes it, because of the shape of it and the muscle and the tissue, the natural physiology of it, it has this natural pacemaker that can beat and pulse with this frequency, with a specific waveform that we understand very well. But sometimes it's effective. And it could be that it's too fast, so we call that tachycardia, or it could be too slow, that we call that bradycardia, or it could be irregular, or sort of maybe some pathway is blocked. It may be regular or maybe chaotic in nature. So many problems with this vital organ. So for that, for a long time, we've had a pacemaker. So basically a electrical device that they put between your muscle here in the chest and the heart, close to it. And this basically measures the heart rhythm and basically helps it out if it's not functioning the way that it should. And it's a big piece of metal that looks like that with leads, and it has a battery inside. And in today's, with the newer batteries, it's lasting about 12 years. And at 12 years, you have to go and they take it out and they put a new one because the battery has run out. So we'll see a block diagram of that. Let's actually take a look at that. But first a picture, so you can see where normally it lies and is connected to this chamber here, and it looks something like this. So most of it is the battery, okay? Most of this part here is the battery. And the electronics are actually highly integrated. So these are not like a bunch of chips. This one single chip that is integrated that we can design with VLSI technologies, and not so much for the cost, but because of the size. Okay, what really dominates here is the battery. But one of the main attributes of this chip here is that it's a very low power chip. Very low power chip. It's supposed to last on that tiny battery for about 10 to 12 years. So in a sense, it is an ECG. So basically it has the same electronics and front end of the machine that is taking your pulse, that is actually, you see in the hospitals, that is coming up with the waveform. It has to have the front end anyways, because it has to acquire that signal to determine how to help the heart. So there is that front end, and there is a filtering, amplification. So the usual electronics that we are used to, we have to filter out the main source, the main content of noise in the human body is actually 60 hertz from the environment. So all medical devices, the first thing that they do is they have a very good 60 hertz noise suppression filter. So it's really a notch type filter where you are trying to take out the 60 hertz. But that's the biggest contributor of noise in the human body. We pick it up from the wires. Okay? So it looks sort of like that, right? So pick up the signal, the front end, we filter, amplify, compare with what needs to be, compare what is with what needs to be, and here we send or generate a synchronizing pulse that is sent back to the heart to help it and keep it on rhythm. That's what's called a pacemaker, because it's trying to keep that rhythm that maybe the heart doesn't have naturally, trying to correct by giving it other stimuli. So It's all controlled by some type of microcontroller and the battery. And another important part is this voltage source supervisor. Okay, so that's a classic pacemaker. Okay. So what we want to do is see what is being done for the future of this technology. So Medtronic is a leading medical device designer and manufacturer in the United States. Very successful company. So they are working on a tiny pacemaker. So look at the difference of how it's going to look. This is going to be inserted via a catheter. So no more open chest incisions, none of that. So this device is going to latch itself into the flesh with tiny claws and be right there. Instead of being here and going with the wires, then it's just going to be right at the heart where it needs to deliver these pulses. The cell is going to do the same thing, but it's how efficiently it's going to do it, how much better, and the other stuff that we can get out of it. So then the physicians can wirelessly monitor and control the device from an app. So right here in that, and we know that if you're going to communicate with the phone at that range, there is Bluetooth involved, okay? Which is being used for more and more things like, remote controls, for example. Nobody uses IR anymore. It's all Bluetooth, the remote controls. So right now we put a pacemaker in there and we hope it works. And if it doesn't work, we know because the patient is not getting any better, or is not sensing the benefits. So it's anecdotal. But here, we're getting data right from the device, And then in the next slides, I'm going to show some of the process so you'll see that it's not so circuits oriented, it's more systems oriented than the previous block diagrams, very circuits oriented. We're going to see a systems view of it. But we'll do that next time. I'm going to stop here for now. All right? Thanks.